Welcome friends to the Formula Engineering classroom, and in this lecture we'll understand the concept of hydrostatic force on inclined plane surface. So let's suppose we are considering this is the free surface of fluid here, that I'm considering this one, and up to this point is the level of the fluid, and let's consider I'm considering a inclined plane surface. And obviously in this case the face of this inclined plane surface is towards the free surface, means this face of this inclined plane surface is towards the free surface of this fluid, and let this plane surface is inclined at an angle alpha from the free surface of fluid. So obviously this is the side view. Okay, now if we view this plane surface from the top, so it will look like this one. Let's just a minute. So it will look like this one. I'm taking the arbitrary plane surface here, so it will look like this one. This is the top view. So the face of this plane surface is towards the free surface. Now to solve this type of case, let try to solve this case according to previous case, that is the vertical plane surface. What is that meaning? Let's suppose this free surface I'm defining surface OO, and I'm considering an imaginary plane surface, sorry, imaginary free surface of fluid that is exactly perpendicular to this plane surface. So let I'm considering a free surface of fluid, imaginary. Obviously this is imaginary here, that I am using this color. This is imaginary plane surface. Okay, and this is at 90 degree to this plane surface, and let this is O dash here. Okay, so first we will try to solve this case according to this one, then we will convert this case according to this actual free surface. So okay, so let's suppose we are considering a strip here over this plane surface of that area dA, and obviously in this case this is we are considering here, so this is dA here. So let's suppose in this case this plane surface is at a distance y below the actual free surface of fluid, and this surface that we are saying this is L distance below from the imaginary free surface. Okay, this is y distance below from the actual free surface, and this is L distance below from imaginary free surface. Now that we are saying this is the center of gravity of this plane surface, so obviously we can mark like that. So around here is the center of gravity of this one. So obviously we know that is we can mark that is center of gravity distance from the free surface of fluid, we can write yc. Okay, and let from this imaginary free surface we are saying this is lc. Okay, so now the pressure distribution over this plane surface, obviously according to the depth of this plane surface from the free surface of fluid, so obviously this point is higher and this point is lower point here. So this at this point the pressure will be higher here, and this point the pressure will be less here. So let's suppose if we are saying that I'm considering like that, so at this point according to hydrostatic law we can say that this is the pressure intensity. Okay, and now according to Pascal's law, the pressure at a point will remain same in all direction. Pressure intensity at a point remains same in all direction. So the pressure intensity normal to this plate at this point will also have same magnitude, but in this direction, that is normal to the plate. So that I'm saying this is P here. So this is equal. Now similarly, when the depth is going to be decreased, the pressure intensity is also going to be decreased. So here this is the pressure intensity, and at the free surface this is going to be decrease up to 0 point. Okay, so this is the variation of pressure. Okay, so now we want to calculate first the hydrostatic force. After that we'll calculate the position of that force. So we are saying at this depth y the pressure intensity is P. I'm saying this is P here. Okay, so we can write P will be equals to, so P is obviously equals to, we can write, so P, this is y distance below, and let W is the specific weight of fluid, so we can write this is W y. It's a simple, or you can also write this is rho G y. Okay, due to this pressure intensity, okay, or let first let I want to convert this y in terms of L. So we know, let here I'm drawing another this diagram roughly here, and if I'm saying this is y and we are defining this distance is L over here, this is L, and this angle is alpha, so I think we can write that is L sine alpha is equals to y. Okay, this is L sine alpha is going to be y here, so we can replace this y here, so we can write this is also equals to W, this is L sine alpha. Now this pressure intensity is according to this imaginary free surface of fluid. Okay, so what is the elementary force exerted by this pressure intensity over this elementary area dA? So easily we can write that is elementary force dF will be equals to the pressure intensity into the elementary area dA. So the pressure intensity is this one, that is WL sine alpha into dA. Okay, so this is the elementary force. Now, so what is the total force? So for total force we can integrate this one, so we can write that total force F will be equals to, so integrating dF, so obviously W is constant here, alpha is also constant, so sin alpha is constant here. Let if I'm taking some particular value of alpha, so this is constant value, so we can take this value out, W is out of integral, sin alpha is out of integral, and we can write this is LDA. Okay, now as I defined in the previous cases, that is integral YdA is defined as first moment of area about the free surface of fluid. Now this integral LdA is also first moment of area, but as L is the distance from the imaginary free surface, so this is the first moment of area about this imaginary axis. Okay, so we can write, and you can also consider the previous cases here, we can write that is integral LdA will be equals to LCA. What is LC? LC is the distance of center of gravity of this plane surface from this imaginary free surface of fluid, that is LC. So from here we can write F will be equals to, so we can write this is W, so this is LC sine alpha into A. Okay, I'm just substituting this value integral LdA by LCA. Now again, so as we are defining YC is the distance of center of gravity from the free surface, and from this imaginary surface this value is equals to LC. So I think we can also say that that is this LC sine alpha will be equals to this YC. Okay, we can write LC sine alpha is equals to YC. So we can replace this value. So we can write F will be equals to WYCA, and yes, the formula is again same as it was in previous two cases, that is force exerted by the static fluid on inclined surface will be equals to WYCA. So formula in all three cases will remain same. That will be equals to WYCA. Okay. Now let understand the concept of center of pressure. That is the point of action of this force, hydrostatic force WYCA. So again we will calculate the center of pressure by the use of concept of moment, principle of moments. So first we solve the moment about an axis that we are considering O dash O dash, that is moment applied by the elementary forces about this imaginary axis, and after that we will use the total force and calculate the total moment exerted by this total force about the same axis as we done in the case of vertical plane surface. So let just a minute, I'm using this space here. So let first we are saying there is this elementary force, that is WL sine alpha dA. This is exerting over this or normal to this plane surface. So I'm saying this is the elementary force, this is exerting over here. This is the elementary force dF, and this force has a distance L from this imaginary surface O dash O dash. This is L over here. So this force will create a moment about this surface O dash O dash, that will be equals to, so we can write this is dm will be equals to df into L here. Okay, so what is df? So df is this value. So we can write that is dm will be equals to, so we can write this is w sine alpha dA, and I think one is L is here, another one is here, so we can write this is L square. Okay, so this is the moment exerted by this elementary force about this imaginary axis O dash O dash. So by integrating this moment we can calculate the sum of the moments by the different elementary forces about this axis. Okay, so we can write that is this total moment M will be equals to integrating this dm, so that I'm taking common, or this, taking out this w sine alpha and integrating L square dA. Okay, now again we discussed this integral L square dA in the previous case, and we defined this is termed as moment of inertia about the axis O dash O dash. So I'm writing this one, so I'm writing M is equals to, moment will be equals to, so this is W sine alpha I O dash. I'm writing O dash because I'm taking this moment of inertia about this imaginary free surface. Okay, so this is our equation 1. So this sum of moment about this axis will also be equals to the moment exerted by the total force about the same axis. So the total force is this one, so I can also write that is M, because this value will be also M, so M will be equals to F into, now this F will act at the center of pressure, and obviously in this case we don't know where the center of pressure, so let's suppose we are considering here is the center of pressure, and let distance of the center of pressure from this axis O dash is let LP. Okay, and here let I'm saying around here is the center of pressure, and from the actual free surface that I'm saying this distance is YP. So but we are solving this problem about this O dash, so this total force is exerted over here, then this F, and this has distance from the O dash is LP, so this will exert a moment that will be M will be equals to F into LP. Okay, so what is F? So F is this one, so we can write this is WYCA LP. This is our equation 2. So the moment by the equation 1 and moment by the equation 2 will be equal, so we can equate them, so we can write this will be equals to, that I'm using this space also, so that I'm writing this is YCALP is equals to W sine alpha IO dash. Okay, so W is out here. So LP will be equals to, IO dash sine alpha divided by this term, that is A YC. Okay, now by the use of parallel axis theorem, we can break this IO dash. So the moment of inertia about this axis O dash, that is IO dash, will also be equals to the moment of inertia about the self axis, that is passing through this one, center of gravity, plus area of this plate into distance, that is LC square, from the imaginary free surface O dash. So I can write this IO dash will be equals to, so I'm writing IC is the moment of inertia about the self axis, plus A LC square into sin alpha divided by A YC. Okay, now we can convert this LP and LC in terms of YP and YC. So like this, L sin alpha equals to Y, LC sin alpha equals to YC. I can also write LP sin alpha is equals to YP. You can say here that around here is the center of pressure, so this is YP, and distance of the center of pressure from this imaginary surface is LP. Okay, so by the use of this one, we can write YP. So YP is what? So LP is what? LP is equals to YP by sin alpha. So I can write this one. This is YP by sin alpha equals to, so this is IC plus A. So what is LC in terms of YC? So LC will be equals to YC by sin alpha. So we can write this is YC by sin alpha square into sin alpha and whole divided by A YC. Okay, so let simplify this one. So from here we can write this is IC sin alpha divided by AYC. Okay, we can write this one, and I think there is also, let first multiply the sin alpha here. So we can write YP will be equals to, so I can write IC, so this is sin square alpha over here, then plus A YC square divided by sin square alpha, and this is also sin alpha and this is also sin square alpha, and this whole term is divided by A YC. Okay, so this term is out. Okay, so and this is AYC and this is this one, so we can write this is A is out and this is here. So we can write this one is equals to, so this will be equals to, oh sorry, actually this is not here, over here there's also this term divided by, so that this is not here, this is only divided by this one, this is divided by A YC. So their remaining term is YC, so I can write YC plus, so this is IC by A YC sin square alpha. Okay, so this is our YP. So we can write this one, that is YP is equals to YC plus IC by A YC sin square alpha. So this is the distance of center of pressure from the free surface of fluid. Okay, so let finally conclude all three cases. So first we defined a horizontal plane surface submerged in static fluid. Okay, so we defined horizontal plane surface in static fluid, and in that case I am defining this is yc. So in this case we defined F is equals to WA yc. A is the area of this plate, and we define in this case yp, that is center of pressure or point of action of this force, is equals to the yc in this case. So this yc is also equals to yp because here that this is g here. So this was our first case. Second case, we discussed that when a vertical plane surface that like that is submerged in static fluid, so we can say this is our yc, this is g, and somewhere here we defined the yp, and the force in this case was WAYC, that was the same in this case, and we defined yp is equals to yc plus ic by ayc. Okay, now third case, that in case of inclined plane surface. So let's try to draw this one. That is inclined at an angle alpha. So we defined this is the center of gravity of the plate, so this is our yc, and somewhat here we are defining our center of pressure, and this distance is yp. So in this case we define force will be equals to WAYC, so force is same in all three cases, and yp will be equals to yc plus ic by ayc sine square alpha. Okay, so in all three cases you have to remember only these two formulas. You can solve all three cases by using these two formulas, because let if I'm saying the force is same here. So if we are saying that is, if the center of gravity of all three bodies, let if the area of the all, let this is the same body, let's suppose we are saying this body is same, and let the center of gravity distance of this body from the free surface is same, means I'm saying in all three cases the yc is same. So for all three cases the force exerted by the fluid will also be same. Okay, but the position of or the center of pressure or the action point of this force will be different in all three cases. So you can conclude by this single formula, means if we are saying let alpha is 0, means the position of this plane surface is the first case. So in that case that whole term is going to be 0, that is ic by ayc sine square alpha, because alpha is 0, so sine alpha is 0. In that case the yp will be equals to yc, so as we discussed in the first case. And let if alpha is 90 degree, so this is our second case. In this case this plate is 90 degree tilted from the free surface, so this sine square alpha is going to be 1. So the formula becomes yp is equals to yc plus ic by ayc, that is this formula. And if some arbitrary angle is given, that is alpha, in that case you can put this value here and you can find out the value of yp. Okay, so for all three cases you only have to remember these two formulas and you can solve all three cases by using these formulas. Okay, so I think the point is clear, and in next lecture we will discuss some problem, and after that we will solve the last case, that is the hydrostatic forces exerted on the curved surfaces. And after that we will close this chapter and we will start our new section, that is buoyant force or buoyancy and flotations. Till then, take care of yourself and thanks for watching. And please subscribe the channel, like the videos and comment your doubt. Thanks again.